So now we have obtained the relationship between, or the equilibrium relationship between y dash and x dash. So whether we can just write as x dash, because this is the general case. So instead of y we can just write y dash and x dash. So now we know a relation equation for y dash, and we have obtained a relationship for, or equation for, x dash, right? So then what we can do is to substitute these values in our new equation. The equations that we obtained earlier for y dash and x dash is going to be substituted in our new equation A, the relationship between x dash and y dash with respect to its equilibrium. As a result of that, we can get the equation in this manner. Even though this one is bit complex, this is just substituting the relationship or the values that we obtain for x dash and y dash. So all these terms are there. So now what we have to do is to simplify this one a bit, and as a result of that we will get this kind of a equation. Now there's no need to remember this equation, but one should know how to obtain this one, the procedure, the method that was used to obtain this relationship. Why? Now look here. Now in this situation, what are the things in here? There's xf, right? So xf is something that we know. Why? Because it is the concentration of our feed. So feed is something that we introduced to the column, so we know our xf. Then there's xd. So we know our, what is the xd. Why? Because we are designing a distillation column to obtain a certain desired product. The concentration is decided by us. It is not decided by someone else. So it is decided by us. So as a result, we know what is xd. And then what is left there is q. So q is something we know because we are the one who is introducing the q, or rather the feed. So the q depends on the condition, the physical condition of the feed, whether it is at the boiling point liquid, or whether it is saturated vapor, or whether it is partially vaporized liquid, whatever. Depending on the physical conditions of the feed, the q value depends. Then what is remaining here? Alpha and Rm. So alpha is something known. It is the relative volatility between the two components. It depends on the temperature, but still we can find it out. So what is remaining there is the Rm. So what we have doing is to find out Rm. As the beginning, it was said that the Underwood has developed this technique to find out the minimum reflux ratio using analytical method. So finally we have obtained an equation with terms of minimum reflux ratio, and while we know the other terms, we know what are the other terms. So as a result, by putting or by substituting the values that we know here, then we can easily obtain the minimum reflux ratio for that system. Now look here. So as I said, that is the general equation to calculate Rm. So we always like to simplify our equations under certain conditions. For an example, when q equals 1, so we know that if the feed is at a boiling point, That means if the feed is saturated liquid, then Q is going to be 1. So when we substitute Q as 1, then our equation will be simplified in this manner. So as we know all these values, it is just a matter of simple calculation to find out the minimum reflux ratio. For a feed at boiling point and virtually pure overhead product. Virtually pure overhead product means we are going to get 100% pure product from our top, or our top product is going to be 100% pure. So it is virtually pure. Practically it is not going to be so. So if it is virtually pure, then XD can be written as 1. So now here X, or the Q equals 1, XD equals 1. As a result of that, we are going to get much more simplified equation. Or the next term is Q equals 0, where the feed is saturated vapor. Then by substituting 0 instead of Q, this kind of equation can be obtained. You can actually substitute this equation for our general equation and see what is going to happen. And then finally our feed is saturated vapor, while we are going to get a virtually pure product from the top. So then our equation is going to be something like this. So now we know that our reflux ratio, the operating reflux ratio, can be varied between the maximum reflux ratio and the minimum reflux ratio. So the maximum reflux ratio is going to be infinite. So when the reflux ratio is going to be infinite, we will get our minimum number of transfer units. On the other hand, we are going to get a finite or a minimum reflux ratio. So when we are going to get a minimum reflux ratio, then our number of transfer units are going to be infinite. Therefore, R is, or the reflux ratio, is going to be operated between infinite and the minimum reflux ratio. Usually it depends on, actually it depends from situation to situation. So this kind of rule of thumbs, this kind of practices are there in industry. So once we obtain the minimum reflux ratio, then we can say the optimum, the operating reflux ratio can be like 1.2 to 1.5 times of minimum reflux ratio. So obviously this is an economic consideration. So if we plot a graph between the reflux ratio and the number of transfer units in this manner, when the reflux ratio is going to be infinite, we will get our minimum number of transfer units, right? But here we are going to get this one, right? On the other hand, when we are going to get the minimum reflux ratio, then the number of transfer units is going to be infinite. So we are going to get this kind of a equation where it will not come into this line. It will go to the infinity. Both these parts will go to infinity. So we cannot operate in these situations. So this is the area that we can operate, or the operating reflux ratio. So that is what we said. It usually can be find out within this range. It depends on the economic aspects as well as the many other considerations. But for now, this you just have to remember that this is how we are going to find it out, and for you these kind of things will be given. So from now here we have finally find out the analytical method to find out the minimum reflux ratio, and then from that we can find out the operating reflux ratio depending on the situation.